Hey all, and welcome to a new video of the Particle System series. So in this video we are going to see how to do a couple of things. First, we are going to see how we can make our particles animation independent of our frame rate. So it doesn't matter which frame rate we got, the particles will always move at the same speed. Then we are going to see how we can change the opacity of the particles on their edges, on the borders of the particles, in order to apply then some blending. Great. And then we're going to see, using kind of the same technique, how we can apply a colored border to our particles. So if we do something like that, we can apply a colored edge to our particles. And then this technique can be applied to a lot of other things. So great, let's dive in. This is the patch as we left it last time. So the first thing we are going to do is to make the animation frame rate independent, which means we can make our frame rate as much as we want. The animation is always going to go at the same speed. So let me get the attribute for the frame rate, FPS. By the moment is 120, which is connected actually to the refresh rate of my screen. But for some of you, the refresh rate of your screen could be 60. So if I will set this to 60, now, as you can see, the animation goes much slower. If I will set this to 30, then it goes even slower. So it's actually calibrated to run at 120 frames per second. But there is a way to make this independent from our frame rate. So the first thing we need is to get the delta time between each frame. So the time that passes between each frame. We can do this by using the object jittime.delta. This is an object that is inside the jitter package, I believe. Exactly. So we can go here in mode, it's delta by default because we created an object called jittime.delta. It's basically jit mode time with the delta mode as an attribute. So this gives us the automatically, because it's already drawing to our rendering context. Let's actually specify this by saying draw to TF particles. And now it gives us the time that passes between each frame. Cool. Now if we send this as a parameter to our shader, u delta time, and let's connect this to our prepend object here for our transfer feedback shader. So we are inside our transfer feedback shader. Let me get it. There it is. So let's create this parameter inside the shader. So param name u delta time. We say u because it's a uniform. Type. It's going to be float because it's a float. Oh, forgot. An equal. And default doesn't really matter because it's anyway going to be updated at every frame, so let's just say it's 0. And then let's actually bind it to our program. So bind param u delta time program. Let's bind it to BP, which is our vertex program, the only shader we got here. Great, let's now declare it. So uniform float, it's called u delta time. Great. So what do we have to do with this, with the delta time? Basically, we want to multiply this value for the movement that the particles do at every frame. So let's explain this with a drawing. So let's say this is our particle, and in 1 second this particle arrives here. So 1 second, 120 frame, the particle arrives here. If we would have only 60 frames though, the particle will only arrive here in 1 second because it will make the same movement for every frame. So if we halve the frames per second, then the particle just makes half of the movement. So let's say, for example, that our particles makes a movement of 1 unit per frame. So in 2 frames, it arrives at 2 units. So if we will have only just 1 frames per second, it would arrive at unit 1. So if we multiply this by the time passed between our frames, so we had 2 cases in which we got 1 frame per second or 2 frames per second. So if we got 1 frame per second, it means that the time passing between each frame is exactly 1 second. So we will multiply this by 1, let's say. So we will have that the particle makes a distance of 1 for every frame. And then if we will have the time between the frames, in this case it will be 0.5 seconds if we have 2 frames per second, then the particle will do a distance of 0.5 per frame. Which means if we got only 1 frames per second, the particle will arrive at 1. If we got 2 frames per second, the particle will still arrive at 1, because the movement that the particles does gets multiplied by 0.5. I hope this was clear enough. It's actually a very simple concept. Probably he'll explain, but I think you got the idea. So we need to multiply actually this value first for the acceleration. But that's actually not enough, because we need also to multiply this value by the output velocity. So we need to multiply this both for the acceleration and the velocity, because of the nature of our algorithm, which involves using the velocity coming from the previous frame. So normally we will just need to multiply this by the output velocity if we were not summing the input velocity as well to our current velocity. But since we are also using the velocity from the previous frame, then we also need to multiply the acceleration for this value. So now it should work, but as you can see, all the particles stop. That's why we need to adjust this delta by changing here the speed attribute of the JIT time delta. We can actually create a float, and we need to make this pretty big. Let's say 140 maybe, because it looks about right. So let's say load mess 140. And actually, thanks to this number, we can change the speed of our animation without touching all the other parameters. So this is just kind of the general speed of our animation. Great. So let's now check if this works also for the other frame rates. If I go to 60, seems to work exactly the same. If I go to 30, gets a bit stuttering, but actually works exactly the same. Let's go 30, 60, 120, 400. Seems to be working. Great. So the first part of our tutorial is over. Let's now get to the second one, in which we create a border for our particles. Now, first of all, let's go in our render shader. So the shader here, the green one, is our render shader, which is just imported into Visual Studio Code. And let's actually create a uniform. So param name, and let's call it this uParticle size. Exactly, it's going to be a float. So with that value, we'll be able to change the size of our particles. Let's make default 1.0. Let's then bind it so to our vertex shader. Bin param u particle size program vertex program. We are binding this to the vertex program, not to the fragment program. Good, so let's declare it here after the model view projection matrix. So uniform float u particle size, and let's use this to actually multiply the value of the mass that we are sending from the transform feedback shader. If you remember, the fourth value of the velocity buffer is actually the mass of the particles we are setting these here. Right? So in this way, the mass is connected to the size of the particles. But in this way, we have also a way to make these particles bigger or smaller using a uniform. Let's create a prepend object, prepend u particle size. And let's touch this to the prepend param, and then to the shader, of course. And let's see. So now they're very small. Now they are bigger. Let's make them fairly big. Great. Let's go back in the shader and let's get into the fragment shader. So we saw last time how to make the particles round. We're using the length of the GL point code, which basically are like normalized coordinates, we said, and when these normalized coordinates are greater than 0.5, then discard actually the pixels, so we just see a round shape. Great, let's actually abstract the length as a variable. So the length of the GL point coordinates, which are exactly like normalized coordinates for every particle. Let's call this length and set is equal to the length of the GL point chord, minus 0.5 to center it in the center. So we'll do exactly the same. Great. Then let's actually say, so else, for example, else if the length is greater or equal than, for example, 0.4, let's even open a couple of graph parentheses. Let's say color.rgb is equal to a vector 3 that we can choose ourselves. For example, let's create red, the color red. And let's check. Great. Now our particles all have a little edge, a little red edge of exactly 1/5 of their radius. So we could also change this using, for example, a uniform. So let's say param name u particle edge color. This is going to be of type vector 3. Default, let's make it black. So 0.0, actually without 0 point, right? Let's bind it. I will just copy that. Put it here. U particle edge color. Great. Let's go in the actually it must not be tied to the vertex program, but to the fragment program. We want this to be in the fragment program. So let's go in the fragment program. Let's create a uniform vec3 u particle edge color. Great. And let's actually replace this vector with this value. Great. Then from our patch, we can actually create, for example, like a swatch object. And let's just get the first 3 components, so red, green, and blue. The 4th component will be the alpha, and let's say prepend. Actually, we can just add this to the message and say u particle edge color. I believe we called it like that. So let me try. Yeah, great. Now we can change the color of the edge of our particles from our patch. Very convenient. Great. There is also another trick that we can do using kind of the same technique, which is to say, let's comment this out. Let's say that the color, the alpha of our color, for example, we could make it related to a smooth step function. So we could say, for example, so let's say that this is our particle seen from the side, let's say, we could say that the alpha value goes between 0, so here it's 0, this is going to be 1, and 1 according also always to the length of the coordinates of the dot. So let's see it actually from the front. So this is the center of our GL point chord. So this is the vector that represents the length of the coordinates. We can see that when this is, for example, greater than 0.3, for example, so between 0.3 and 0.5, so the value of the alpha channel will follow a smooth step function, so I can go between 1 to 0. Great, so let's try this in practice. So this will work like this. Let's create a smooth step function. So we could say between 0.2 and 0.5 of the length. When the length is smaller than 0.2, it will give us a 0. When it's greater than 0.5, it will give us a 1. So exactly. So let's reduce the speed of our animation drastically. Actually stopping our animation, right? And let's make the particles bigger. Great. So you can see that nothing changes because we don't have blend enabled. So let's actually create a message. So let's say blend enable $1. Probably we need also to disable the depth, but let's check first this. Cool. So now it's the other way around. You can see that we basically made the inside of the particles disappears. So in this case, will give us at 0 when the particle, when the length is less than 0.2, and then we make this curve going up to 0.5. So basically, it's the reverse of that, and then it will give us the value of 1. So this also looks pretty cool. But if we want to invert that, we just need to say 1.0 minus that. And now we got the inverted thing. Let's make them a bit bigger. Cool. Let's actually disable the depth. So like this. Depth enable. We need the opposite of that. So we just cannot do it like this. We need to create another message and say depth enable $1. Connect this to the GGL mesh and just subtract 1 to that. Basically, so we just subtract this toggle to the number 1. Great. So in this way, the depth now is disabled, and you can see we have a nice effect in which the edge of the particles is nicely blurred out. Great. We could also assign these values to some uniform, of course. If we try to say between 0 and 0.5, then we get it even more blurred. So in this way we give it kind of a center that is kind of solid, and then make them blurred on the edges. Great. Let's try to put our animation speed back to 140. Great. Make our particles a bit bigger. So let's maybe make it in a way that we can switch between our edge and alpha thing. So we could do it in the most efficient way. Well, actually it doesn't matter. We can actually just uncomment that. Right. Makes this bigger. So if we activate the blend enable, it's not going basically to take into account our edge color. If we deactivate it, then it's going to take into account the edge color. So let me check that. Yeah, basically it works like this. Cool. So we have a new nice feature for our particles. Cool. Next video we're going to see how we can keep the size of the particle correct according to how far we are from the particles. Because by the moment they're always the same size, doesn't matter how far or close we are, the dots on the screen are always the same size. So this is actually could be something uncool, and we will fix this in the next video. If you want, you can add kind of a variable, a uniform, to take this effect out. So you could make, for example, an if statement and say, if this value is true, then do that, otherwise don't do it. Alright, so you could use a uniform for that. This will be the assignment for the next video. Great, so thank you very much for following, and let's keep having fun with the particles. See you soon in a new video. Ciao, ciao.